Good evening, everybody. Thanks, Bob, for inviting me. So here I'm going to briefly talk about my research and also my commercialization aims about biodegradable plastics from organic waste. So just a bit background of myself. Now I work for University of Aberdeen in the School of Engineering. I've been doing research on general biological processes, on renewable energy and process engineering for over 25 years, both in the university in Rome, where I come from, but also in the industry in the UK. And currently, I'm in the process of starting a spin out from University of Aberdeen. The aim is to commercialize our processes, essentially to convert organic waste into valuable chemicals. Here I will talk about particularly plastics, but we are not interested just in plastics. We are also planning to make organic chemicals and hydrogen. So far, we have been doing these things at lab scale, and now we are seeking funding for scale up. So the problem we are trying to solve is that for the vast majority, chemicals and plastics nowadays are made from fossil resources, and this contributes to CO2 emissions and climate change, because essentially we are embedding the fossil carbon into the chemicals, into the plastics. At the end of the chemicals and the plastic life, inevitably this fossil carbon will be released as CO2. Instead, if, as we're trying to do, is if we make these chemicals and plastics from organic waste, any kind of organic waste, then eventually CO2 is also released anyway. The carbon in the plastics, in the chemicals, will have to go to CO2 at the end of the day, inevitably. However, that CO2, if we are going from biomass, that CO2 is recycled when the biomass grows, when the biomass that then turns into waste grows. So it's a net zero cycle from the point of view of CO2 emissions. So this is just to say, we hear a lot talking about CO2 emissions. CO2 emissions mostly come from energy, from burning fossil fuels for energy in the cars, for electricity, for heating, etc. But it's not just that. So actually, fossil resources are everywhere. It's not just energy. Fossil resources are in chemicals that we use in everyday life, even in drugs like paracetamol. We use all paracetamol when we are ill, but paracetamol is made from the feedstock is a fossil resources, is petroleum derivatives. So if we think about shampoos or washing up liquids, it's not just the packaging that comes from fossil resources, but it's also the active ingredients that are ultimately made, in most cases, from fossil resources. Even cosmetics, we wouldn't think so, but normally most of the active ingredients are derived from fossil resources, from petroleum derivative, of course, after reactions and purifications, and packaging as well. Fertilizers, of course, we cannot grow crops without fertilizers. This is ammonia fertilizer. Well, ammonia is NH3. Where does the H come from? The H comes from hydrogen. And where does the hydrogen comes from? It comes from natural gas, again, a fossil resource. So everything nowadays comes from fossil resources, and we want to change this. I mean, for two reasons. One is climate change, CO2 emission. The other reason is that fossil resources are finite, are limited. Sooner or later, we are going to run out of them. Or in order to explore them, we might have to, I don't know, find them in the Arctic, in the deep of the sea, which cause also all sorts of other environmental problems. So our vision is that we want, this is the current situation, where we start from fossil resources and we make chemical and plastics. We want to move from into renewable feedstock and renewable energy to make sustainable chemicals, sustainable plastics. Now, when I say sustainable, it's very important to say, sustainable is a very complex, sustainability is a very complex matter. It's not just, I'm from engineering, but certainly it's not just engineering. Engineering, also science itself cannot give a definite answer about sustainability. Sustainability is a lot of social issues. Sustainability is politics. That's all fine. I can make something that is zero CO2 emissions, for example. I can make something that entirely from sustainable resources. I can make something from biomass. I can use entirely renewable energy, but that doesn't necessarily mean that this is sustainable, because this something that I'm making can be very toxic for the environment, can kill fish, can kill people. So in that case, even though it's made from renewable feedstock and renewable energy, still is not sustainable. This is just to say that sustainability is very complex. We certainly in engineering, in science, we are not all the answers. But talking about plastic now more specifically, with plastic, there is another issue with conventional plastics, is that normally they are not biodegradable. So if you think about polyethylene and other plastics, they're not biodegradable. That means they accumulate in the environment, which is another problem. And also organic waste is generated in large amounts. So in particular, I'm going to talk about this type of bioplastics that we are interested in making, which are polyhydroxyalkanoates. And essentially, these are the empirical formulas here compared to the polyethylene, which is a conventional plastics. So the good thing about PHAs is that they have physical and mechanical properties that are similar to conventional plastics, and they can be made from biomass, while instead polyethylene comes from fossil resources. So first of all, PHAs in reality is not a new material. We are certainly not inventing them. PHAs already exist. They are already on the market, but in very, very niche markets, very tiny amounts compared to the millions of tons of other conventional plastics. And PHA are made normally from virgin biomass, from sugar cane, from sugars, by aerobic fermentation with pure cultures, etc. And these are some PHA products that are on the market. We can find them online. They are not certainly very, say, common, but they can be made they can be used to make many plastic products, bottles, cups, food containers, etc. However, the issue is that nowadays this is much more expensive than conventional plastics, and because they need virgin biomass, they need specialized processes. So our invention, so to speak, or the things where we have been doing research for a lot of time is making this plastic not from virgin biomass, like from sugar canes or from crops like corn, but making them from waste, like food waste, manure, agrochemical waste, and so on, to turn them into plastics. So essentially, this is our invention, so to speak, to put it simply. So essentially, it's a new process to make the PHAs from organic waste. The good thing is we can use any biodegradable organic waste, like food waste, manure, mixture of them. And another good thing is that here, at the end of their lives, the PHAs can be recycled back. They are biodegradable. They're relatively easy biodegradable. They can be recycled back to anaerobic fermentation. Here can go back into the cycle, so to speak. So essentially, our solution, we believe, has various commercial advantages compared to conventional plastics, and we plan only to use renewable energy, again, to further reduce our carbon footprint. We have done an economic analysis for a full-scale, hypothetical full-scale process. This is for an ideal plant that will convert 100 tons of per day of organic waste. This is more or less, roughly speaking, when I came up with this figure of 100 tons per day of organic waste, is in the ballpark figure of the amount of food waste that is generated by a city of Aberdeen. So every day, 100 tons per day. And so we're making so I did some cash flow analysis, and the process seems to be profitable with considerable profits. Of course, at the beginning, we have to put some capital expenses. So this is our business model for us spin out. So we're looking for funding for to investment to us to build a pilot plant, to make the first sale, and then we plan to move to commercial scale plants. Just I want out to say something about the physical and mechanical properties of PHA versus conventional plastics, because of course this is a key to the applicability, because PHA chemically they are different from from conventional plastics. Like conventional plastics are polyethylene. Here we have the low density, high density polyethylene, polypropylene, polyethylene terephthalate, the PET, and the PHAs. So first of all, these are average properties. PHAs are really slightly different molecules depending on the nature of the waste, etc. So this is a sort of average properties. These are the young modulus, which is quite high. This is here I'm just saying that the properties of PHAs are comparable, in some cases better than conventional plastics. Here we show high stiffness, of high rigidity, so it makes this good for packaging materials. And also it's relatively good. PHAs are relatively good. We see them in blue here. Relatively good in terms of ability to carry loads. Not as good as maybe like the PET, but relatively good. But however, one downside of PHA is that they're relatively brittle. If you so, this is the elongation and break. How much we can stretch the plastic. Not much for the PHAs. In terms of oxygen permeability, this is another important thing for if you want to use for food packaging. We don't want the oxygen to permeate the food packaging, otherwise the food might rot or might be compromised. So PHAs is better than many materials currently used, except PET, which is better. But so in this case, low is good. I just want to finish saying that in reality, PHAs are not the only bioplastics on the market. Another important bioplastic that in reality is much more common nowadays than PHAs is PLA, which is polylactic acid, that is used to make also is used to make already some plastic material like glasses, cups, and so on. Polylactic acid is also a polymer that comes from biomass. Normally, it is done in similar ways as current process for PHAs. It is done from is made from sugarcane. Sugarcane. We have the sugars. We extract the sugars, then we use the sugars as a substrate for the fermentation, making lactic acid that is then polymerized. So PLA is a very good material. Here are some analysis of the properties of PLAs compared to PHAs and the other plastics. You will see that in terms of strength and rigidity, if you look at the graphs on the top left and top right, you see PHA is among the best materials, in some cases better than PHAs in terms of rigidity, of ability to carry load. So, and that's why PLA is used. However, PLA has some limitation. It is even, if you look at the graphs on the bottom, it is even more brittle. It doesn't stretch, essentially. Is the worst in terms of stretch, in terms of flexibility, is worse than PHAs. And in terms of oxygen permeability, this is the oxygen permeability. We have said that PHAs and PET are very good. PLAs worse than PHAs, but better than polyethylene. This gives us an idea of the applicability of this material, but I would say that both PLA and PHAs are generally applicable as material and have the advantages of coming from biomass. However, one limitation of PLA versus PHAs is the biodegradability. So PLA, sort of polylactic acid, we say it's biodegradable, but it's much less biodegradable than PHAs. Well, one thing is interesting. PHAs are polymers that are made by microorganisms. So the PHAs are made by the microorganisms themselves, and we need to extract them. Therefore, they are very biodegradable because the microorganisms that are in the environment know what they are. So to simplify the matter, PLA is not made by the microorganisms. The lactic acid is made by the microorganisms, but then we humans, we polymerize it. So in a sense, the PLA is much less known to the environment, to the microorganisms, than PHAs. And this is the fundamental reason why PLA is less biodegradable than PHAs. For example, essentially PHAs also degrade in the open environment, while PLA essentially only degrade under industrial composting conditions where you have 60 degrees, a certain type of microorganism, and so on. For example, PLA normally does not degrade in the home composting, while PHA does. So and also, so the bottom line is that with PHA we can have a full recycle of the plastic packaging at the end of their life. So as I showed before, PHA can go back to anaerobic digestion, and from anaerobic digestion we can make new PHA. With PLA doesn't work that way. With PLA, recycling is possible and is good. However, PLA needs to be separated from other plastics in order to be recycled, while instead PHAs can work with mixed waste. And it is much easier to work with a mixed waste than with a waste that needs to be separated from others. That's all that I wanted to say. Thanks for your attention. And these are some products and companies that make PHAs. Yeah.